Hi, my name's Tom, and today I'm presenting alongside my teammate Sam for our under-actuated class project titled Stabilizing LQR for a Quadruped with Hydroelastic Contact. Gradient-based trajectory planners, unlike hybrid contact techniques, do not require an explicit definition of the mode sequence for locomotion planning. However, high-fidelity contact models can pose challenges for these solvers. One way to investigate the feasibility of gradient methods on a robot is to apply stabilizing LQR. In class, we learned how even a high-dimensional system like Atlas can be balanced using LQR, where the foot was replaced with a pin joint to remove the contact mechanics. In our study, we wanted to understand whether it's possible to linearize the contact dynamics of Little Dog as an initial step towards gradient-based planners like ILQR. To understand why contact poses an issue for linearization, we can look at the manipulator equations. External contact forces are a function of the contact Jacobian, or direction of the contact forces, and the force magnitude. Contact models can often lead to non-physical discontinuities. As seen on the bottom left, a point contact model results in a discontinuous jump in the contact force, posing a problem for gradient-based solvers. A recent modeling approach available in Drake is hydroelastic contact. This approach is analogous to the buoyant force exerted on a submerged body, as contact is computed as a surface integral which depends on penetration volume. Hydroelastic contact can yield a smoother evolution of force, and therefore we wanted to investigate whether it can be linearized on Little Dog. Here we show our simulation setup in Drake. We begin by identifying the fixed points of the system and defining our hydroelastic contact properties. We perform a Taylor expansion about the fixed point, which allows us to define a corresponding LQR controller. And finally, we add destabilizing force perturbations to the diagram. We also characterized our model for a range of contact parameters and evaluate LQR at multiple fixed points in this system, including three-legged standing. Now I'll hand it over to Sam to discuss our results.
The outcome of this setup is a system that can stabilize about a fixed point through contact forces, in which we can apply perturbations to and see its dynamic response. With this, we decided to evaluate the effect of contact model type and contact stiffness in the stability of the Little Dog LQR control, comparing between hydroelastic and point contact models and varying the ground contact stiffness for each. As you can see, the hydroelastic model is able to withstand larger perturbation forces before failure compared to the point contact model, which is expected due to its more continuous response. We can also see three distinct regions in the hydroelastic contact case. So there's a soft region in yellow where the contact is too soft and the feet sink into the ground. There's the rigid region in blue where an increase in stiffness has no effect, and then the variable region, which in green there, and where the maximum force has a nonlinear relationship with ground stiffness. Finally, we also wanted to explore the effect of varying target fixed points as a step towards time-varying LQR. So we did this by defining three distinct fixed points. There's the standing, leaning back, and leg lifting poses seen here, and then we created a separate LQR controller for each. So by wiring them up to this custom system in Drake, we're able to switch between the controllers mid-simulation, and we get a system which you can see here, which is able to stabilize about these three distinct fixed points using LQR. So then we decided to use this to demonstrate the concept of sequential actions, since the leaning back pose serves as an intermediate step that allows smooth motion. So you can see here, it's essentially a bridge between the stable layout and functions of the standing and leg lifting controllers. So as you can see, removing this intermediate step causes the robot to jam its leg. So conceptually, this means the standing pose is at its sort of the border of the leg lifting LQR controller, the controller's region of attraction. So we can take the learnings from here to apply in the future to an iterative LQR approach to solving gate optimization problems. And with that, thank you very much.